The last question we'll consider during the development stage is how can you ensure that your model is fair? While this topic is still being researched by ethicists and computer scientists, a general way to think of unfairness in ML is a model that exhibits discriminatory bias, perpetuates inequality, or performs less well for historically disadvantaged groups. But it's important to realize how the term discriminate can be used in different ways. Technically speaking, all machine learning discriminates, since it just means it's able to distinguish or differentiate, and the word classification means to discriminate. And when we're talking about fairness, in this case, we're concerned with wrongful discrimination. Wrongful discrimination typically involves disadvantaging people in protected classes based on characteristics that you see listed here, like age, disability, medical history, sex, race, and so forth. In US law, wrongful discrimination falls in two categories: disparate treatment, where membership is, in a protected class is used as an input to the model, and decisions are differentiated on the basis in a way that disadvantages members of a protected class. And disparate impact, where outcomes of the model disproportionately disadvantage members of a protected class. However, given the unique features of AI, it has proven difficult to show how cases of unfairness might fit into these two categories. So instead of focusing on how AI can be considered unfair, we'll now look at different metrics that have been devised to help promote fairness. One metric is group unawareness. Sensitive attributes like race or gender are not included as features in the data. A benefit of this metric is that it avoids disparate treatment. But a disadvantage is that there may be highly correlated features that serve as proxies for the sensitive attribute that end up producing discriminatory results. So we got to watch out for that too. Another metric is called group threshold. We counteract historical biases in data by adjusting confidence thresholds independently for each group. So if group A has typically been disadvantaged relative to group B, we might decrease the confidence threshold for group B, so our model doesn't unfairly exclude members of this group. A potential problem for this metric of fairness is reaching agreement about the existence of historical bias, as well as how the confidence thresholds should be adjusted accordingly. A third metric is demographic parity. Here we are concerned with the positive rate being equal across groups. Suppose we have a health wearable device that predicts if someone is healthy, and the employer is using this to model as a basis to offer bonuses. In this case, we might want all individuals to have equal rates for positive results. But now let's take a closer look. If one group is more qualified and so more likely to be healthy in our example than the other group, then achieving equal positive rates might mean that we have to exclude some qualified members of the advantaged group. And this raises concerns about reverse discrimination, as you may be familiar with the debates about affirmative action policies. The fourth metric of fairness is equal opportunity. We want to make sure that among the people who are actually qualified, so actually healthy people in our example, that they have an equal chance of being accurately classified as such. So we are primarily focused on the true positive rate, or the relationship between true positives and false negatives. So for example, over here, group A, there are 9 true positives and 3 false negatives. So our true positive rate is 9 by 12 or 75%. For group B, we have 3 true positives to 1 false negative. And our true positive rate is 3/4, or once again, 75%. But if we look closer, we might notice that we've introduced a lot of false positives for group B, and this might be problematic in certain contexts. The last metric of fairness we'll discuss is equal accuracy, where the percentage of correct classifications as actually healthy or not should be the same for all individuals. This refers to the overall accuracy rate of the model. The problem that might arise is that even when the accuracy rate is equal for group A and group B, the errors that end up occurring may be different for each. For example, in group A might have a higher false negative while group B might have a higher rate of false positives. If you remember from the previous video, we talked about the bias with the North Point's recidivism tool. This is what ended up happening when Black defendants had a higher rate of false positives and white defendants enjoyed a higher rate of false negatives. When the model's results inform decisions about the distribution, of some benefit or harm, differences between false negatives and false positives can make a big difference. While you might think that the right thing to do is to satisfy all these metrics as best as we can, researchers and CS have shown that we cannot do this, a problem known as the Impossibility Theorem. For example, group awareness, where we don't consider sensitive attributes, is incompatible with group threshold, where we set a confidence threshold independently based on the sensitive attributes. And equal opportunity, where the true positive rate is equal across all groups, is incompatible with equal accuracy, where accuracy rate is equal across the groups. Now that we've covered different metrics for fairness, we'll focus on some other tips and tricks to mitigate unfairness in machine learning. One common pitfall is referred to as the framing trap. Typically, designers operate within the algorithmic frame, where they consider questions like whether the properties of the output match the input and whether the algorithm provides good accuracy on unseen data. That's what we've been focusing on so far. But this is only one important lens through which you evaluate your model. We'll also want to consider the data frame that we talked about earlier, where you consider whether the bias has been removed from the training data and whether the demographic information requires optimization through one of the fairness metrics that we discussed. Lastly, we'll want to consider the socio-technical frame. How does the model operate when considered as part of a system of humans and social institutions? For example, you might design a fair algorithm for predicting health that satisfies an appropriate metric of fairness. But if the employers who use this model to inform their decisions about handing out bonuses routinely, they ignore the recommendations of this algorithm or don't consider it completely, then your model might indirectly result in unfairness despite how you've optimized it. Another common pitfall is the portability trap. It's commonly regarded as a benefit, where you can reuse your algorithm from one context to another, right? We talk about generalizability of your model and not overfitting it. For example, you may develop a TinyML algorithm to aid water conservation efforts in California in the US and optimize it for fairness. But since the model is successful in this context, we might think, maybe we can similarly use this in Nigeria, in Africa. But context matters. Repurposing algorithmic solutions may not preserve fair outcomes. And similarly, if you're training, like say, autonomous vehicles to drive in San Francisco, and then we say, oh, let's put them in Beijing, the traffic rules are different, the way people drive is different, the cultural expectations of driving behavior is totally different. You're not going to have the same kind of safety record over there. So you'll always want to do your research before deploying your model in a new context. The last common pitfall we'll cover is the formalism trap. If you're working on machine learning, you might think that the ultimate question needs to be answered, is which mathematical formulation of fairness should you use? But, another important question to ask is, in which social groups, you listen to and then include in your deliberation. As focusing on just one social group might give you a conflicting result, with the best metric for fairness than if you had, focused on a different group. So while issues of fairness can be tricky and researchers are still making progress in this area, it's becoming far easier for individual designers to tackle, this issue on, how to deal with fairness, thanks to publicly available tools like Google's What If tool, which allows you to explore, different metrics and help you optimize fairness for your model.